So we started with y equals beta naught plus beta 1 x. We found estimated. We got a model y hat equals beta naught hat plus beta 1 hat times x. And theoretically, we stick with the formula or whatever derivations we had for beta 1 hat and beta 1 hat, because both of them are unbiased estimators. Long time ago, I mentioned what an unbiased estimator is. Do we remember? Is an estimator an accurate representation of whatever parameters that you're trying to get? By accurate, I mean 100%. No, it's called an estimator, so it is an approximation. But what does unbiased mean state? You can look in your notes. Take parameter. Loud in the tires. And I can't hear you.
Its expectation is the parameter itself.
So expectation of the estimator would be equal to the true value without any bias. There is something called bias variance. It's done in, especially these days, machine learning and stuff. There, the terminology is slightly different. They call it as overfitting, underfitting. Here it's bias variance. Similar manner, expectation of beta 1 hat must equal beta 1. Or must equal beta 1 if you have an unbiased estimator. I showed you a long time ago, both of them are unbiased. So, great. But what does it mean? What does expectation mean? I said, if it's confusing, you just replace it with things like, so that's 162. What does an expectation have? Do you cover expectation yet? Expected value. What's the formula?
Would be the sum of the variable times its corresponding probability.
The sum of is it the sum or the integral? I mean, never mind, I don't want. Sum of x multiplied by the distribution of probability. Good. So informally, you can simply think of it as putting a sum and then dividing it by the sample size polygon. And that sum divided by total number of observations is simply sum everything, divide by the total, the mean, right? So what we're saying is, in the long run, if you keep on getting a larger and larger and larger sample, eventually beta naught hat, using the formula that we have, would equal to the true value. That makes sense in the long run. But how large of a sample should you get to get the exact value? It's not possible, but theoretically, what is the condition? Sort of have the answer earlier. The only way I could guarantee an exact value where the estimator matches whatever truth you have is when the sample size matches the population size, which would defeat the purpose of statistics. Anyway, it's not feasible. Unless you want to waste time the rest of your life. That said, whatever we are going to find here is not an exact value. rather it is a mean response. On average, this is what one would expect. For that reason, some texts might write the original model as mu sub y equals beta naught plus beta 1 x. I believe your book uses it somewhere. We put a mu because mu is a standard notation for me from 2023. Why do I put a mu? We put a mu because the model is going to give you an average or mean response rather than a response. Good. Okay. So whether you call it as y hat, mu sub y, mu hat sub y, one in the same. This is more formal. I don't want to bring this earlier because it could be confusing, which is why I put it on. No. Why specifically now? Well, the entire purpose of fitting a linear model is to infer something about the relationship that you have. Suppose someone comes up to you and says, well, I have a value x sub 0. We had a set of x values going back to our example. We had 5 x values. Suppose I just picked x up 0. And what was the range of our x values? 1 to 5. Yes, let's take 2. Now, our case here is discrete. So we can only go from 2 to 3, we can't do 2.5. Can't go to a restaurant 2.5 times. In practice, if you have continuous answer, you can take 2.5, whatever value, as long as it falls within the observed range of x values. Good? Okay. On average, what should one expect? Well, that value denoted by mu hat, you're finding y when x is equal to x naught. Now, we have done this before. This has a name.
Regression analysis.
What? Dennis, can't hear you.
So it's a linear regression analysis.
Great. Don't think like Dennis. When you plug in x is equal to x naught in here, you're going to get a number. It has a name. I used this name before. Blank value. Blank starts with the letter F. Fitted value, very good. So that is simply the fitted value. Even though this is a fitted value, we are putting a new meaning to it because the theory of regression simply suggests that you're not simply getting an exact value, rather you're getting an average response, a mean response. This will have variation on its own. Do you agree? Everything's got very good distance. So we need to find the variance. What is the variance used for? From earlier today, from last time, we made use of variance to find something time and time again. starts with the letter C. Confidence interval. So variability gives us confidence interval. So we want to find the variance of that. Plugging in x is equal to x naught. Yes. What is beta naught hat? We derived this a long time ago. So beta naught hat is y bar minus beta 1 hat x bar. If you recall, when we derived, we first found beta 1 hat, then we plugged in to find beta naught hat. And that's just how we did the example was. We first found beta 1 hat, then we found beta naught hat. Plugging in beta naught hat plus, and then if beta 1 as is, x naught is simply the value that I'm going to use. Variance of y bar, and
But then we also just found the variance of another one. Like we also just found the variance.
that's exactly where I'm going. We can directly apply the variance of beta naught hat and beta 1 hat. I'm doing it this way because later on when we do the centered case, it will make better sense. So y bar plus. Did you understand Matthias' point? Or what he said? I plugged in beta naught hat in, right? His point is why plug in beta naught hat? I could rather use the variance of beta naught hat and beta 1 hat directly. Sure, you can't, but I'm doing it. Beta 1 hat, then I could write the last part as x naught minus x bar. Agreed. Okay. Key thing to know, whatever value that you pick is going to be away from the mean of all the x values. Do you agree? We have 1, 2, 3, 4, 5. I believe that was our x values. The average is 3. If I picked 2, 2 deviates from 3 by a unit of 1. Good. Now, variance of 2 random variables. 3162 people. How to now write it?
Plus the square of x naught minus x bar.
And boom. Okay. So he gave the answer already. Well, I'll split it. So what are the properties of variance is that if you have variance of x plus y, you can split them up as long as x and y are.
You can split them up either way, which is up to left. Variance either way.
Exactly. If you have a direct relationship between the two random variables, there is another term, but you can split them up without any issues if they are independent. Here they are. Matthias gave me the answer to this part. Also, let's see if you paid attention to Matthias. How can I rewrite that? Close. Very good. You know, you understood the property, but let me just make a point here. So of these two, that is the random variable, right? beta 1 varies. That is a value that I pick, which is fixed. The average of x's, independent random variable, doesn't have noise. So that's the constant. That's it. How would you write it? Random variable, constant. Let's see. Very good. So variance of y bar plus all the constant after variance, it becomes square. X naught minus x bar square. Variance of beta 1 hat. Good. We derived this already. What is the variance of beta 1 hat? Eric,
R times sy over sx.
the variance of beta 1 hat, the one that we derived, sigma squared divided by sxx. Yes. What is the variance of the average of y values? 2023, variance of the sample mean. 0.
Constant.
Constant.
Sample mean is a constant. It's our sample.
To do it this way. Y bar, I can write it as sum I equals 1 to n, yi divided by n. Yes? Do we agree that y is a random variable? Okay. I can pull the sum out. Do you agree? And I can split them up without any issues because y's are independent, our assumption. So I can take the sum out. Second term. X naught minus x bar squared times sigma squared over sx. What is the variance of yi? Yi is random. Yi has variability introduced by the noise. What is the variance of noise? 1.
So follow the normal.
Sigma squared, right? Day 1, variance of y is sigma squared. Why is it sigma squared? Variance of the noise is sigma squared. What causes variance in y? The noise causes variance in y. So that variance is simply sigma squared. There is n here. Now, property of variance. If I pull that 1 out, what would I get?
Over n squared.
1 over n squared. Variance of y, sigma squared. Sigma squared is a constant. Yes. Assuming n of them.
Then it's cancel out, you get sigma squared over n.
So 1 over n squared times n sigma squared. Running out of space. You did write that side down.
Yeah.
The n would get cancelled. You will have sigma squared over n plus x naught minus x bar squared. Sigma squared divided by sx. Good. 2023. Sampling distribution. the mean of the sampling distribution for sample mean is the population. The associated standard error is S over square root of n. If you have a good estimator, theoretically, that would be sigma over square root of n. If you square sigma over square root of n, you would get sigma squared over n. But that's where this comes from. I have sigma squared in common. And that is the final formula for variance, for the expected mean response. Can I erase this down? Well, x naught is a value that we are interested in. We know how to find SXX. We know how to find x bar, and it's given a problem. How do we find this one? Using the data, what gives us an estimator for sigma squared? We just did it earlier today.
Expected minus observed squared.
Which is mean squared error, MS spreads. So the variance estimator for the expected mean response is simply the estimator for sigma squared, which is MS squared, times 1 over n plus x naught minus x bar squared over SXX. Good. Now that variance is actually the standard error that we use in confidence intervals. Because we're talking about a mean response. Now that we have a standard error for the mean response, you've got to multiply it by something to get the margin of error. What is that something? How did we find the margin of error for beta 1 and beta 0? Standard error times constant one, but do the same thing. To find the 100 times 1 minus alpha percent confidence interval for the expected mean response, I take the estimator for that, which you get by plugging in x naught in your fitted model. You add the margin of error and you subtract the margin of error from the fitted value or the mean response. I did not throw the words mean response earlier because it would be confusing. This is why I'm waiting this one. I even grew a couple of grey hairs. No. So shut up. E is the margin of error. How do we find that? We simply multiply the critical value. Forget about the notation. I'm going to write it as 1 minus alpha over 2, comma, df. What is df? Well, generally speaking,
N minus 2.
n minus 2 times, is it that or the square root of it? Square root of that. So simply sigma hat of the mean response. Good. So once we find the margin of error, you add and subtract from the fitted value, and we can conclude 95% of the time, the average response would lie between that number and that number. Good. Okay, we'll do an example, or we'll continue our example on this next time.